Cool. I'll start that.
Yeah.
Cool. Well, Prashant, thanks for joining us. You've got a very small quorum today, but I think it's because it's a Wednesday. So, um, uh, uh, people have work or whatever. But I'm really excited to see this presentation today and then to see it again in like a week when I meet you at IEEE LangSec. And I think both of us are kind of thinking along similar veins at the moment in terms of like both what problem are arising because of LLMs that are solvable via LangSec perspectives, tools, etc. And also what can we do in LangSec using LLMs is interesting, right? So I think that some of
Yes.
what you're talking about today is like in line with these broad questions, and I'm excited to see what you have to say about it.
Yep. Thanks for inviting me to do this. This is exciting. So you are aware of what the overall problem here is. So there's the category of problems where the parsers themselves may have bugs, versus the categories where there may be two different parsers that are meant to do the same thing, but they don't. Like, for example, there are plenty of these PDF insecurity kind of bugs where you might have two readers that show different content, or one shows that a PDF is signed, whereas another says it's not. A big deal was with the kind of bugs that Dan Kaminsky had reported more than a decade ago, where they found that you could inject these null bytes inside X509 certificates, and then one browser would show one thing, whereas another would completely think of something else. And then how these certificates get validated, there are disagreements there too. And HTTP request smuggling, where the kind of middle box or proxy has a set of rules it's supposed to follow. For example, you can say that /.ssh is a path where I, for some godforsaken reason, store uh, my SSH private and pub key, but I don't want it to be accessible through the middle box on the server, and I kind of blacklist that that path, and then a middle box or a load balancer like Google will say that, okay, if I encounter this path, I'm gonna not allow it through. And then there are some ways that you can bypass these using HTTP request smuggling, because Google processes HTTP requests a certain way and someone else would do it another way. And the whole suite of Pegasus and Paragon attacks are entirely focused on, as an entry point at least, entirely focused on like malformed image files or PDF files, where you have a malformed image file and then it does something funky. It doesn't really, there's no piece of logic actually validating the image entirely before the processing starts.
Which I should mention in case we post this recording and somebody watches it, that you were also involved with our Pegasus event, and people can go back and watch the recording of that, which I think was
Yeah,
probably the best event we've done so far. Yeah.
that was a great panel with a very esteemed set of panelists. And this is the 150th talk. It may
Yes.
not end up being the 150th recording, uh, depending on whether this makes it. But yeah, so in general, the approach that people take over here is you usually roll out your own parser, you roll out your own cryptographic implementation, but of late, there have been plenty of these tools that have come about, Antler being one of the most popular ones for programming languages, where you can, instead of building your parser from scratch, you just give it a grammar, and then the parser generator would go from the grammar to your actual C++ or Java or Python implementation. Antler supports a lot of these languages, and then some other really popular data description languages, or DDLs as I'll call in the rest of the talk, are Kitai Struct, which is a really popular one for data formats, where you can describe your data format in a YAML syntax. DFDL uses XML. I'll reserve my judgment there. Parsley and Daedalus are newer ones that were actually built as part of the DARPA SafeDocs program. And Parsley was built by SRI International, and Daedalus was built by Galois. And DFDL is one of the more unique ones over here. It has this capability to also deserialize input. Actually, I meant serialize. So you have an input, you go to an AST, and then from that AST, you go back to the input. So for example, you have that intermediate AST on which you can make some transformations. You want to redact some data. you see that there are some IP addresses there. I want to redact that IP address so that when I pass it on to someone else, it doesn't identify where it's going. So you can do those kind of operations in DFDL. I meant serialization there. The other paradigm over here, which is also extremely popular for parsers, is to create smaller parsers and combine them using choice operations. It could be ordered choice or equal, and it could also be sequence operations. And then this kind of paradigm is called using parser combinators, where uh, you just write your parser directly in the target programming language, and you don't have the need to learn something entirely new like you do with parser generators, where you need to learn the grammar syntax as well. Hammer is one of the new incoming parser combinators. It's been around for the last decade, and it has bindings in several languages. It's written entirely in C and C++. And norm is available in Rust, and both of these target like binary data formats in principle. So I want to give you all like some examples for what these DDLs and parser combinators might look like to just give you a feel for what the syntax is. So what I have here is an IPv4 header packet, and that's the image that you see over there. It's from the RFC. And the hammer parser over here goes from the total length field all the way down to the destination IP address sequentially. Uh, the weird thing over here is probably the B67, that's the byte 6 to 7, which includes the flag and fragment offset. That's the weird thing over here, but you'll see that essentially you have this combinator, which is to parse unsigned 16-bit integers or unsigned 8-bit integers. And then you also have a repeat operation over here that allows you to, the repeat operation over here that allows you to have a repetition of 4 8-bit unsigned integers. And that's the syntax over here. And you have the overall combining operation, which is the sequence. This is the norm syntax. There's a little more complex, but not really. So it's essentially the same thing, just saying that it's a big endian unsigned 16-bit operation. And then you have a sequence of these. They have a different address operation over here for IP addresses, and that's not a part of this code snippet, but this is just Rust. And then you have some of these more esoteric ones like Daedalus, where you have a struct operation for, and inside that struct you have all of these sequences. And I'll say that the norm and hammer ones were things that I wrote, whereas the Daedalus and the other ones I'm going to show are all things that are available on their own code repositories. So this is the Kaitai struct one. You'll see that this also contains the B67 one. And the reason that hammer has it is because I use this to generate that. And essentially, this one is, again, a little bit easier. You have the big endian unsigned 2 bytes, and then the sizes over here are all in bytes, whereas most other DDLs use the number of bits. So for example, U1 would be 1 byte, but they also have like B1, which would be 1 bit. So, and they byte align their fields as well. So if you have something that is just B2 and then you have 6 bits missing, then they'll just byte align it.
And can you do dependencies? Like, can you make the checksum a checksum if you want to?
Yes, yes.
Okay.
You can. So you can have, yeah, there are ways to do it. You can essentially define a separate function of sorts and then have the checksum calculation over there. And that would run in parallel once you're parsing. Like once the sequence ends, it would check the checksum. Yeah. You can also have if conditions over here. So like after the type U1, you can have an if over here to say protocol needs to be equal to 1, for example. Because it's an unsigned integer, you can just treat it as an integer. If it's a string, then you'll have to do some typecasting and then do the same check. So Kaitai struct is extremely popular. It's probably the largest format gallery. It has like 60 plus formats. So a lot of these are available there. DFDL, I think this is a bit ugly, but it's essentially XML syntax, and pretty much can do most of the things that the other DDLs can do as well. Just that it's a little verbose to write and not much of IDE support for this. And Spicy is one that comes as a part of the Zeek intrusion detection system. It's probably the simplest syntax that you can find among the special purpose uh, DDLs over here. So the primary approach that people take to write these write these like data descriptions is you have a specification that you need to read and analyze manually, and then you start implementing parsers for that particular specification. And you could use a DDL or a combinator, or you could just directly implement it in the target programming language. And you also want to have like a corpus of real world data that you can evaluate your parser on to ensure that you are covering most of the corner cases that might be there. And then in general, there would be some things that you miss, and then you want to improve your parser based on what that data looks like, and whether there were a lot of valid files that you missed, or there were some corner cases that you missed. But there's also this weird case where you could have done something that, so there are some formats for which the specification came uh, after the format was already out there for a bit, like PDF. So then there are numerous cases like this where you implement the specification strictly, and then you realize that the specification missed some cases that are observed in the wild. So then you could report those and fix things in the specification like the way we did with a PDF a while ago. But in general, you wouldn't really encounter this, but PDF is like a special case where you would. And that's an easy way to like spot errors in the specification document itself. And we are all using Copilot a lot. A lot of engineers are using it on a daily basis. So we wanted to see if this particular manual process that is used to go from specifications to like parsers could be actually automated for some of these data description language syntax. And so with that, we asked a few research questions. So the first one was, we wanted to see if off-the-shelf LLMs could produce DDL code that is syntactically valid. And then we wanted to know if this generated DDL code covered 100% of the format specification. And we wanted to see if it was rejecting inputs that we knew was malformed, just a bunch of bytes randomly. If you inputted that to your DDL generated code, your generated DDL code, would it reject it? And then we also wanted to see if the LLMs did not really know about the syntax of the DDL. Can we actually teach it using either example specifications or using the manual document? So of course, we also started with some hypotheses. One hypothesis that we made, the first one was that LLMs must be able to produce some sample specifications. We thought that this should be possible because when we prompted them for some of these formats, like it was able to produce something that resembled the DDL. Unless you run a compiler on it, you don't really know that it's valid. But visually, when I was first just using the chart interfaces, I thought it was producing something that looked valid. So this was the first hypothesis. The second one was that I assume that these specifications are pretty large and confusing, so the LLMs would tend to miss some portions of it, and they wouldn't be able to accept all the valid sample inputs that I have in place. And then I also assume that that these specifications would be quite permissive and accept like several of the malformed inputs that I try to throw at it. These aren't really crafted in any way. Like there's nothing special about them. I just used a mutation fuzzer for them. So I just wanted to see if the specifications are actually strict enough. And then finally, I thought that if you did provide specifications and manuals, they should be able to provide compilable specifications as an improvement from what it was providing earlier. So here's the pipeline that we built. We took the format, so we created prompts and we had a list of formats. And then we also had prompt templates that I'll show you in a bit. And then we were sending these prompts to the black box off-the-shelf LLMs. And then the LLMs would produce DDL outputs that we would store in files, and then we would try to compile it. And if it wouldn't compile, then we would send the error messages back and ask the LLM to fix it. And then we would try this loop 3 times on top of the initial prompt. And then we were also like, once we had a successful compiling specification, we were then checking if the specification was actually correct by running binary input files that may be valid or invalid. And then the other things to consider over here was that we looked at 5 different temperature settings that were between 0 to 1. You can ask why we did this. We just followed prior work that was at Oakland and stuff. But there were also several papers that we came across that said it shouldn't really matter for most programming tasks. And that's pretty much what we found as well. So these are the prompts. I don't expect you to read through the whole thing. There's nothing interesting over here. The first prompt over here is just to ask the LLM to like list all the fields that are in that particular format specification. And then the second one, in the same context, we were asking the LLM to generate a DDL specification for the format. The third one, which is a part of the loop, which was asking the LLM to like take the error message and then improve the specification in the same syntax. And the reason that we have output and DDL over here is because, for example, something like Kaitai, we want to say Kaitai specification in a YAML format, just so that the LLM knows that it needs to produce valid YAML output, or DFDL in XML format, for example. So that's why we have like these values over here. And we also had 2 other prompts over here, one to go from samples to a specification, and then to provide the manual itself. So then that's why we have a manual attached, and then can you generate DDL specifications from that?
Prashant, you had to generate the entire new spec one shot, right? Not like a diff or something.
Yes.
Yeah.
No. Yeah, so that's why we had to stop at 3, because if you don't want to use RAG or some other interesting tricks over there, you just want to keep it simple and within the same context, then anything beyond 3, we were running out of
Yeah, that makes
context
sense.
windows. Yeah, so future work, yes, we should use smarter ways to actually manage the context over there. So here's essentially the kind of models we used and the parsing technologies we evaluated and the formats. So you'll see that the models are not the most recent ones. And the reason for that is that we submitted the paper in the middle of January. Yeah, in the middle of January. So then we used the ones that were most recent then and that were available. Our one came out like 2 to 3 days before the paper deadline. So we could have added it. We had the scripts ready, but we just didn't want to take a chance and have to regenerate all the images and stuff. So that's why you'll see that the models are a little old, but that's also because these things do move pretty slowly and pretty quickly. And the paper was submitted in the middle of January. And among the file formats, you'll see a lot of variation over here. There are a few that we eventually focused on for the rest of the evaluation, but at least for the initial check to see if things even compare, we evaluated all of these. And HL7v2, if you're not familiar, is a healthcare data communication protocol. Like that's how you pass medical data. Same for DICOM over here as well. So here you go. We actually evaluated the how many examples were even compiling. So the first 2 that I'll show over here are Spicy and Norm. So Spicy is its own data description language, and Norm is in the Rust syntax. And you'll see that for Spicy, there are, other than ARP, pretty much everything else, the accuracy levels are pretty low. And the columns over here that we have are Gemini, GPT-4 Turbo, GPT-4o, Claude Sonnet, Claude Haiku, DeepSeek, and Llama. Uh, and I'm pretty much using the same set of labels for all of them, for all the images going forward. And what you'll see over here is that ARP is pretty much the only one that you'll see a high number of compilations. So there are 5 for each cell. So you go from 0 to 5 based on the if it has 5 over there, that means that all the 5 temperature settings that we tried was successful. And then Claude Sonnet over here pretty much had the most number of compilations. And you'll see something really drastic for norm. In general, all the LLMs were able to produce compiling specifications, essentially because they probably have a lot of Rust examples, and they're aware of the syntax that Rust uses pretty easily. So this was like an obvious thing that we thought would happen. And you'll see that the results are pretty much in line for Kaitai and Hammer as well, where Kaitai uses YAML and Hammer is based on C. So then you'll see that Claude Sonnet pretty much is still the best one that's out there for this particular task, with DeepSeek and GPT-4 Turbo also doing reasonably well. And so essentially, they were all able to produce specifications to some degree. This is where things get a little more interesting. So we also looked at Daedalus, which is again its own data description language, and then DFDL, which is based on XML. And for neither of them, we were able to find many comparing specifications. And the reason I say that is because you'll see 3 over here, 1 for native and 2 for HL7v2. And that was interesting because when we actually went and looked at it, because Gemini in general doesn't do well, so we were curious and we found this message, and that's why it compiles, because it's essentially just a comment that says there's an incomplete placeholder, it's not possible. So this is something that was really common that we saw for both Zeek Spicy and Daedalus that Gemini keeps doing without actually generating something valid over there.
I posted a video, I think it was like 5 months ago. I'm pretty sure I posted on LinkedIn, but basically, I asked Gemini to test an incorrect implementation of isort, and it had access to a sandbox to execute code. And it said, no problem, I tested it and it's correct on all these inputs, and here are the outputs. And they look great. So I expanded to see what it had done. It had rewritten my implementation to be correct and then run it.
Yeah, and that's pretty much what it did on the left, which was the first time Llama. So this is Llama though, not Gemini. But yeah, Llama, like in the first try, it gave me a completely incorrect Hammer implementation, and then fed it all the error messages and said you're wrong. And then it actually got rid of Hammer entirely and produced something that did compile. And Llama did this very frequently with Hammer, whereas the other implementations didn't. So at the very least, if you say use this library for a lot of implementations, the other LLM said, okay, fine, I'll use this library, but Llama was like, no, not doing it. Yeah, as I said, we also looked at the temperature variations, and in general, there was no big trend. In general, like you'll see Claude Sonnet, GPT-4 Turbo, DeepSeek, they all do reasonably well in terms of the compilation percentages. But there's no proper trend over here to say that a particular temperature setting always does better. The lower ones as well, like that's not always true. Sometimes 0.25 does better than 0.0. So you can't really make that generalization. So to answer the other research questions, we looked at a large data corpus called GovDocs for the image files that we were looking at. So it has a lot of files, but most are PDFs and Microsoft documents. So we extracted the images that were available from this particular corpus. So there was JPEG, GIF, and PNG that we were most interested in. For network protocols like NTP, we looked at the Wireshark GitHub repository that has some packet captures. And then for something like Modbus, which is like a power protocol, power automation kind of protocol. Like for that, we looked at we actually got this privately from the New York Power Authority's lab called Agile. and we used those particular packet captures to evaluate our Modbus implementations. And we essentially, the mutation was pretty simple. We mutated it 3 times using a mutation fuzzer. We ensured that it was still invalid. If it wasn't, then we discarded it. And to evaluate ground truth, we used this Python library called Pillow for image files, and then we used Wireshark for network packets. And uh, this is not the best way to do it, honestly, because both Pillow and Wireshark are known to be a little permissive. So not the best decision, but that's the decision we made. And we computed the precision and recall, and essentially an imperfect precision over here would mean that you accept some of the invalid files, and an imperfect recall would mean that you only accept a subset of the valid files that are out there. And yeah, we define parser correctness over here for our use case as we want to hit 1.0 for both precision and recall, obviously. Um, so in this graph, in this table, I'm only showing JPEG, GIF, Modbus, and ARP just to simplify how things look. And you would wonder why there are so many of these NA kind of boxes, and then there are also dashes. So the dashes mean cases that didn't compile at all, and the NA implies that there were no successful parsers at all, which would mean that the numerator and the denominator are both 0. So I can't really give that a value, so it's just 0 by 0 there. And then, so the other cases are the more interesting ones. So we have a 0.0 for one of the things that Llama produced, where essentially that the valid files did not parse at all, but then there were invalid files that Llama did successfully parse. And there's also numerous of these 1.0 kind of numbers over here, which denotes that there were no invalid files that were passed by these implementations. So then you do wonder, how does recall look and for these exact situations? And it does look good for some of them. So there were exactly 30 cases for which we actually saw a precision and a recall of 1.0. So there were many cases where no inputs were accepted despite having a compiling specification. So that's why we saw NA for a lot of the numbers in the precision table. And then there were 30 cases for which there was perfect precision and recall, but none in the hammer parser combinator. So there were 5 GIF implementations produced by Claude Sonnet in Kaitai struct that was valid and correct. And there were totally 25 ARP implementations produced by various LLMs in the Kaitai struct and the norm syntax. And unfortunately, none of the JPEG and Modbus implementations really met the criteria that we had. And I just wanted to show this is something that we just recently generated just to show what things look like. So for something like JPEG, there were totally 105 instances that we tested, and 58 of them compiled. And then there were no valid parsers for 28 of the subset of them, and then there were no perfect precision, and there were no correct implementations. And for Modbus, you'll see perfect precision was there, but then even then there were no correct implementations. And then for ARP, there were quite a few correct, and there were still some that did not really accept any valid inputs at all, any inputs at all, actually, not just valid. So next we looked at, this is the last research question that we had. We looked at providing sample specifications on the manual. So the manuals were often like these large PDFs or a sequence of web pages. So then we had to use either PDF to text kind of tools, or we had to use some kind of a scraper like Beautiful Soup. And then neither really worked because the manuals were usually incredibly large if it were available as a PDF. And so we had to pick a subset over here. So we picked just Daedalus and Spicy because their manuals are much shorter, and the number of compiling specifications for them were pretty low anyway. So then we could actually show that there was an improvement. And we found that the manuals did not really produce any improvement in the LLMs really, because uh, they already knew whatever they knew in the syntax, and then providing the manual and asking them to read it and then answer some questions or produce improved specifications didn't really help for this use case. But then we did find a large improvement in cases where we fed like just 5 sample specifications for both spicy and Daedalus, and we found that for both JPEG and Modbus, there was a pretty big improvement in the number of valid spicy specifications. For Daedalus, this experiment entirely failed. Like it was 0 for the original case and remained 0 for the next one for Daedalus. Like there was no improvement at all. Like the format, the DDL format is quite complex, and we couldn't really do anything about it other than manually creating specifications. So just revisiting the kind of hypotheses we started with. So the first question was, the first hypothesis we had was that all LLMs must be able to produce some sample specifications in each DDL syntax, and that wasn't true, unfortunately. Things like Daedalus, DFDL, and even Spicy to a very large extent, there weren't many valid specifications at all that we were able to produce. And they do tend to miss large portions, and they accept only a small set of the valid inputs. And then we also showed that a lot of malformed inputs do get accepted by these LLM generated specifications. And then the last one was exploring few short prompting to see if we can actually provide some information. And we found that yes, manuals did not help, but a set of valid examples did. So some future directions that either we'll explore or we think the community should. So one thing that we did not explore was patching the specifications based on failing inputs. So as I said, we did have issues with the context window, so this is not something we explored. So if you do encounter an input that causes the parser to fail, can you feed that input back and say where the failure occurred? We also need to use some of these newer reasoning engines to conduct a similar study to see if there are massive improvements in the kind of results that we found. And another interesting thing would be a tool like Kaitai. It uses a YAML syntax, but it's only as descriptive as it is. So then can you use some of the data from the format gallery to translate one DDL syntax to another? Especially if you need to teach an LLM the DDL syntax, can you do this? Is another interesting research idea that we've been thinking about. And finally, there are some file format features as well as some features that the corresponding DDL might have that prevent accurate LLM generated specifications. And LLMs obviously get some things wrong quite frequently. Like for example, in a JPEG format, the kind of syntax that might be there, it does seem to get wrong quite frequently. So can we do a more systematic study to explore what these discrepancies might be, and can we correlate this? So some other discussion items that we were also thinking about. The first thing is the Postel's robustness principle. We used Wireshark and Pillow, but they are known to be quite permissive. So is that really a good measure of ground truth? I don't know. If you use differential fuzzing to compare to more real world parsers, that would be a way forward. But then you need to use a programming language that allows you to gather coverage so that you can mutate input well. So that's still an interesting challenge. We didn't really know how to do it, and that's why we picked the easiest path there, which was to use Wireshark and Pillow. But I acknowledge that that's not the best way here. And there are limitations there. The second one is, while we did release the prompt templates as well as the source code, and we set the model versions, and then we ensured that we have all the sample specifications that we generated available in our GitHub repo. There are still reproducibility challenges. Like even if you just ran the same experiment a bunch of times, there are still some variations. So that's just the nature of using LLMs to do a lot of this work. And then if people are to use LLMs to generate sample specifications, then the recommendation would be to go with Hammer, Norm, or Kaitai struct, because those are the ones for which a lot of accurate specifications are coming out, and uh, at least they compile it. That's the baseline conditions. They do compile at least, and going beyond that, like we are able to find situations where these are correct. Yep, that was my talk.
Prashant, that's super cool. Um, I guess the most obvious question to me is how like LLM difficulty correlates with human difficulty. Like, do you find data lists annoying as hell to write, or
Yes.
is there some discrepancy there?
No, I do find it annoying to write.
Okay.
I probably find DFDL the most annoying, and that
Ah,
did translate pretty well. DFDL is incredibly
interesting.
hard because you just miss, like, it's in general, I don't find XML very easy to use, and DFDL just comes from that. Daedalus is also hard, and the reason it's hard is because there aren't that many example specifications available on the repo. Like if I wanted to
Right.
do something, I would have to like think hard and drink a
Yeah.
lot of coffee to even figure out how to go about it. Like they dealt with PDF, which is the hardest thing out there, but there are still a lot of just simple constructs in network protocols that I don't really know how to deal with. Like a JPEG parser is quite incredibly hard to write in dataless syntax.
Right.
And
That makes
Parsley is in a
sense.
similar boat, and Parsley has even fewer examples. That's why I didn't end up evaluating it in this particular use case. And I did contribute to Parsley.
Okay, cool.
Yeah.
Are there like logical dependencies between lines of code that matter for the LLM? Like, for example, when an LLM writes imports at the top of a file, it is basically planning the rest of the code is going to write, right? So
Mhm.
is that an aspect of what makes some of the specs harder or easier?
I'm not sure. We did look at the lines of code for the ones that did compile, and even for that, we didn't really find anything to correlate with. Like it
Yeah.
was just entirely random
Okay.
when you actually look at the lines of code that it does produce for the specifications that do compile.
Interesting.
Yeah,
Okay. And did you try fine tuning, or do you think fine tuning would make a difference?
I think fine tuning would make a difference. We did not try it, but I do think that it would make a difference, and it's probably a better way to do it than to just feed specifications to it.
Yeah.
That didn't really help that much, and I do think fine tuning would help that.
Okay, interesting. There's kind of this like emerging field now, maybe not in academia, but like an industry of models that are for diff application. And so that was one of the first things I thought of when you were showing like the placeholder content generation or things like that. Is
Mhm.
some of these specs can be pretty big, and I wonder if using some sort of model that's trained specifically for applying diffs and then fine tuning the LLM to begin with to generate diffs.
Mhm.
Um, yeah, something like that maybe could get higher quality results. But I feel like there's only so much juice to squeeze when you're really trying to force something that can't reason to do reasoning, right? So
Yeah, there is only so much juice to squeeze, you're right. And in general, the whole idea was just to see if people are going to do this regardless of whether it's good or bad. We
yeah,
ourselves are trying to do some of these tasks using LLMs. We just wanted to see if it, it does a half decent job at least to get you started. And it
yeah.
probably does. It at least is able to tell you what fields are there, what sequence you're supposed to follow.
Mhm.
It might not, so it does help a lot. Um, but yeah, I did not know about the kind of diff approach that you talked about. Would be excited to read something about that.
Well, we'll get dinner or drinks or something when I'm in San Francisco, and I
Yes,
can show you some stuff.
yes, yeah,
Cool,
absolutely.
awesome. Chris, do you have any questions before we call it? No worries if not.
No, no, I'm searching for the mute unmute button. So no, I'm good.
Okay. Well, Prashant, this is wonderful. Thanks so much for presenting and for being our 150th talk. And I can't wait to see you in a week.
Yeah, should be exciting over there. I'm sure we'll grab drinks.
Sounds good.
Yep, see you soon.
Okay.
Thanks a lot.
Adios.